All right, welcome back, everyone. Uh, Last session, what we were talking about is this idea of a stress tensor. And this is my stress tensor shown over here on the left, or an example of a stress tensor where I have these 9 different cells representing stresses in 9 different directions. So in this case, we said there's a relationship between the stressor. What it represents is what's going on if we look at like a cube on that at the element we're interested in. So how it would look for this stress tensor is I see -10 in the XX direction, so I have this -10 or 10 in compression, and I have the 3 in the X face in the Y direction, and then I have this 2, +2, which is my sigma YY. So hopefully, if you can't yet, you might want to practice going from our stress tensor to the stress cube. Well, today we're going to continue to look at this stress cube and the stresses on our element. And the way we're going to look at this is in essence like the 2D. So if I were looking down the z-axis, this direction, what I would see would be something like this. So all I've done is I've shown what it looks like in a 2D context where I have the 2 KSI pulling on this thing in tension in this Y direction, 10 KSI in compression in the X direction, and I have a 3 KSI shear stress. Of course, all those arrows, those 4 shear stresses are all 3. So that's what my 2D element is. Now, the question comes is what would happen if I were to stick a bar right here and start to rotate this element slightly with all of these forces staying in the exact same orientation. Meaning, if I were to rotate it, say 45 degrees or something like that, you can imagine what's going on with this 10 KSI. Some of it will be suddenly pushing against a slanted surface, so more of it would be transformed into a shear stress, and I'd have a higher shear stress. And these forces and these shear stresses change as my element rotates. Well, here's the thing. Materials don't understand angles. They don't know the X, Y, and Z axis. So any rotation is possible. All we really care about is what rotation, because what we're really saying is what if we rotated our axes? What if I called X, slightly different? There's some orientation that would be the worst case scenario. That's usually what we're concerned with. What's my largest shear stress? What is my largest axial stresses? So to do that, we need a method. And this method that we're going to use today is called Mohr's circle. So what Mohr's circle is a physical representation in a way that, and actually there's some equations involved too, to represent all the different possible shear stresses as I rotate my element around. So let's start by, with this example, just showing you how I would draw a Mohr's circle for this 2D element. The first step that I would do is I would draw some axes. And these axes are going to be my sigma, which is an axial stress, and tau. But the one thing you got to watch out for is we're going to draw our tau axis, positive tau axis, pointing down. So my axis ends up looking a little something like this. And then once I have that axis, I'm going to plot a series of points on this axis to develop my Mohr circle. The first part that I'm going to plot, first point I'm going to plot, is my sigma x and my tau xy. So coming up to my 2D element, my sigma x is this 10 KSI. It's actually -10 KSI because it is in compression, and my XY is 3. Now technically, with the shear stress, the way I have it drawn right now, we consider that to be a positive shear stress. If those arrows were pointing to the lower right and upper left, then we consider it negative, but kind of a smaller technicality that I wouldn't be too concerned with. But I do have to be concerned with tension versus compression. So I have a -10 and 3 for that first point. So I go, let's see, 2, 4, 6, 8, 10, and maybe about here. So that's that point, -10, +3. And remember that that +3 is pointing down. The second point that I want to plot is our sigma y value, and then I'm going to say negative tau xy. So what we're saying is my y value is 2 ksi, and then I'm just going to do the negative of that 3. So plotting that on my graph, I'm going to go over 2, and then I'm going to go up for negative, and probably about here, something like that. And after I have those 2 points plotted, what I can do is I can connect those points with a line, something like that. And here is a key point. We have this average stress, or sigma average, and that sigma average will be the intersection with our sigma axis for our average stress. The next step in this process would be to draw our circle, and with this circle we are going to have our sigma average at the center, and we'll have a radius r, which we'll develop an equation for that in just a second. So I end up with something like that. Now, based on this circle, I can develop my fundamental equations that I can use for the rest of the course. One is, if I wanted to know where the center of this circle is, this sigma average, it is equal to my 2 stresses, sigma x plus sigma y over 2. So for this particular case, what I would have is my average stress, which is the center of the circle, is negative 10, don't forget that negative, plus 2 over 2, which is negative 4 KSI. The second part that I could develop is looking at the radius. And I can get the radius because I could draw a triangle. Either one of these, I could draw a triangle, and I can find the relationship for these sides. And I know that this value over here is our tau xy, and the length of this side over here is sigma x minus sigma y over 2. So hopefully it's just a little geometry. Hopefully you'd be able to figure that part out. I forgot to label this point. I might as well put it in there. This is 2 minus 3. But and you could use either triangle. But developing the equation for that radius, then the radius using Pythagorean theorem would be the square root of that sigma x minus sigma y over 2, that quantity squared, plus tau xy, that quantity squared. And here, for this particular case, our radius is equal to the square root of 6 squared plus 3 squared, or 6.708 KSI. So why do we care? What does it all mean? What it means is, if I look at this Mohr circle, what I have drawn in red here, any point on this circle represents a state of stress, meaning if I were to rotate that element, or I rotate my axes is really what's going on. I might have a point, here and here if I rotate this thing around, and then I can see a much higher shear stress, and I'd have a lower axial stress, and I can rotate it. I have an infinite number of rotational points. But the points that I really care about are the maximums, right? So the points that are most important to me, the points I care most about would be the part here, here, and if I were to draw a line straight up there or there, right? So the rotations that I'm most concerned about, those maximum points, are the largest. So this would be my maximum sigmas, right? And then my maximum tau would be when it's vertical. So let's talk a little bit about how we rotate along Mohr's circle. There's a relationship between rotation on Mohr's circle and rotation of our actual element, if you think about rotating this in theta. So this relationship looks like this. So my relationship is shown here, or if I rotate the element by some angle theta, or wanted to look at that relationship, it's equal to 2 theta on Mohr's circle, or twice as much on Mohr's circle. So and the direction is the same, meaning if I'm rotating my element clockwise, then I'm rotating this 2 theta on Mohr's circle would also be clockwise, right? It's rotating this thing. I could draw it either side, but something like that. So back to our example, what we really care about, like I said, are those extreme values, those maximum values. So let's start by looking at these two stresses on our sigma axis. So like it says here, for our example, we're going to rotate counterclockwise until we reach that sigma axis and say, what does that look like? So looking at our element, we have something that looks like this. This is point 2, -3. This is the center still. And the other thing that I do know here is I know that I'm actually not going to put that 2 -3. What I'm going to put are some dimensions that I know, because I know that this value is 3 high. It's actually -3, but I'm just looking at the values right now because I could be looking at this side as well. And I also know the radius to this, right? So we found the radius to be 6.708. So this is 6.708. And from those two, I could find out the angle that I need to rotate it to get to that horizontal placement. And from that, notice I did label that 2 theta p because I want to know how far I have to rotate the element to get to that principal stress, or that horizontal member. So I know Mohr circles twice as much, so I'm labeling it 2 theta p. From that, I could say that I know an opposite and I know an adjacent. So what I would be looking at is that the sine of 2 theta p is equal to the opposite over the hypotenuse. So what I ended up with is 2 theta p is 26.6 degrees clockwise. Now that's on Mohr circle. That's how far I would have to rotate on Mohr circle to get there. And that means that theta p is actually 13.3 degrees clockwise on our element. So if we look at what that actually means for our element, this is the way our element started. And we are going to rotate it 13.3 degrees clockwise. I guess something looks like this. Now once I rotate it, I want to know what my actual stresses are. So I want to know what my stresses are at this location on Mohr circle right there. Well, I can see shear stress is 0. There is no more shear stress. I've rotated to a point where I only have those stresses, those 2 points. Let's see, I could find these values by using the fact that I know mathematically that those 2 values, I'm going to call them sigma 1 and sigma 2, are equal to the average, which is the center of the circle, plus or minus the radius of the circle. What we have is sigma 1 would be equal to -4 plus 6.708, or 2.708 KSI, and my other stress, sigma 2, would be -4 minus 6.708, which is equal to -10.708 KSI. Now, these have a special name. They are called our principal stresses. So if I were to put these onto my element, I have, in the direction isn't really important, I suppose technically this would be my 10.708. Notice I'm not putting in the negative sign because instead I'm just showing the negative being in compression. And in the other direction I have 2.708. Of course, those are both KSI. So if I look at what's going on with that element, that's my worst case scenario as far as tension and compression. I started off with a tension. So if I were designing this material, I know that I might calculate it that I have to support a tensile stress of 2 KSI, but in reality, the actual stress would be 2.708 KSI. That's what that little element right there actually feels, because it doesn't understand X and Y. And if you rotate your axis slightly, that's what you'd end up with. Same idea with the compressive stress. Instead of 10, I'd have 10.708. Now we need to do the same thing to find out what our maximum shear stress is. So looking at rotating this element, our maximum shear stress is at the top and bottom of this element, or when I rotate my axis to a vertical sense, right? This is my tau max, and now we labeled these as sigma 1. Actually, that was sigma 2 and sigma 1, our principal stresses. So those are the three things we're really concerned about, our principal stresses and our maximum shear stress. So for our maximum shear stress for this element, we're going to rotate 2 theta to our maximum, or to the vertical to get that max shear. And well, we already know how far we'd have to rotate it if we go back to our Mohr circle. We already know what that, the 2 theta p on Mohr circle was 26.6, so to go to the vertical would just be 90 minus that on Mohr circle, right? Meaning I'd have to rotate my element 63.4 degrees counterclockwise in order to get to that vertical stress. Now, the easy part is if we want a value of this maximum stress. Now I'm going to put one little thing I'm going to call it in plane, meaning it's going to be within that XY plane. Next class we'll look at rotating it in the third dimension, but right now we're only rotating it in 2D, in that 2D plane. So our maximum shear stress in plane will always be equal to the radius, which is already solved for, and we can see this right now. This is just the radius, so that would be that height, right? So, so for us, this radius is equal to 6.708 KSI. Okay, I hope you found that helpful. I'll probably add another video. It's real short, showing an example of me solving a problem from start to finish and the process I do, because now that we have all these equations developed, you don't have to do all that work. So look for that. I hope all's well. Let me know if I have any problems, and good luck. Thanks.